Okay, so this was the test that we did so long ago now. So the first one, we were talking about a cost function that was positive, increasing, and concave down. So it looks something like this. So which of these numbers are greater? So is the derivative going to be more at 2 or at 3? Well, since it's concave down, it's going to be greatest at 2, which is going to be greater, the slope at 3 or the average to 3. So remember, the slope at 3 is going to be kind of this slope here, and the average at 3 is going to be this slope here. And that slope there is going to be greater. Also, again, the average is going to be greater at a lower number than a higher number, because we can see that these slopes of these lines from the origin to the curve get less steep the further we go along. And the last two were average costs, but we can think of our average costs as secants, right? So again, secants that occur earlier are going to have a higher slope than secants that occur later. So here is an early secant, and whereas compared to this up here will be a later secant. And so those two things would be the greater ones. So because it's concave down, basically, every time something was earlier, it was steeper. In question 2 was the elasticity question. So the quantity when the price is 20 was 1600. The derivative, right, was minus 4p. So that means the derivative at 20 was minus 80. And so you just put it into the formula, you get 20 divided by 1600 times minus 80. And of course, you've got absolute value side. So the elasticity was 1. In question 3, we had to find these different points. The fixed costs is the y-intercept here. The break-even point was the point where the first point where the revenue goes above the cost curve. So it's right here. The place where marginal cost is minimized, that's the place where the slope of the cost curve is at its least, so it was around here. The point A, where the average cost is minimum, that's that point where you take a kind of ruler and it just touches the curve, and that's that point there. And then finally, where profit is maximized, where is this curve parallel to this curve? And it was there. So we have a logistic curve. We have to estimate total potential sales. So we see where the curve is increasing the most, and it was around here. So doubling that was around 3,900, something in that ballpark, the maximum possible sales. Given costs, and we're given revenue. So when I tell you what the price is, that's actually giving you revenue, right? Because $788 means that the revenue is that times Q. So the marginal cost is the derivative of this. The marginal revenue is that price. And so the maximum is going to be when those two things are equal. You go quadratic and you solve it, 34 and 6. And it turns out that at 34 was the maximum, and 6 is actually the minimum. So here is a surge function. What was the value of B? Well, if you do like find where the peak was, it was around where the time was 4. So that means B was around a quarter. Why would you do this instead of this? Well, if the danger line was somewhere between that and that. This line here, I'm sorry, was just a printing thing. It actually wasn't attached to the curve. Marginal revenue and marginal cost, estimate the production level that could maximize profit. Well, you're going to see where marginal cost equals marginal revenue. It's in 2 places. But this place is a minimum, right? Because we can see that that marginal revenue is less than marginal cost beforehand, whereas this is a maximum. So it's going to be between 2,000 and 3,000, and we actually see that 2,500, we estimate marginal cost to be 75 and marginal revenue to be 75. So that would be the best estimate. And then finally, we see 2 polynomials here. They look like degree 2. 2 exponentials. Here we have exponential decay. Here we have exponential growth. Here's a logarithmic. Here's a surge function. And there's a logistic function. And that was our test. Okay. And so no rest for the wicked. We're going to have a test again next week. It's just going to be on chapter 5. So hopefully that's a kind of like just a nice digestible lump for you to go on. So on Monday, we'll have a lab again. We'll talk about the class. So there are 9 people in the class. So maybe I was thinking of doing 3 groups of 3. Sounds like the best thing to do. So we can think about that. Okay. So 5 is actually pretty easy because all we've got to talk about is go back to what we did in the first lab, and that was when we talked about the average value of a function. So I just want to sort of rehash that again, and hopefully now that makes sense. Okay, so hopefully now this is what I used to sort of to start off motivating what an integral was, and now we can look back at it and hopefully this kind of makes it kind of crystal clear. So when we do an average, we add up something and we divide by the number of things that it has. And so the sort of the paradoxical thing about figuring out an average value for a function is that it's got infinite number of points that we're adding up. So we get an infinite sum divided by an infinite number. But if we do things in terms of area, right? So we sum up all those rectangles and we get an area. And so all of a sudden, something which is infinite becomes something which is a number, i.e. just the area underneath the graph. And now we're dividing by, instead of dividing by something infinite, we're dividing by a length. And an area divided by a length is a length. And so that makes whole sense of what we mean by taking an average. So here, this is a sum. This is sort of adding up all those rectangles. It's kind of adding up all the values of the function. And then we divide by the length of which the integral is on. Okay, so that's the formula. So when we look at a picture, hopefully that makes perfect sense, right? Because here, we have a perfectly nice function. In the blue, we have the integral. We know that the integral is the area underneath the curve. Okay? So we can think of that integral as kind of adding up all the values. It's an integral over this interval. If we go back to this formula, if we take b minus a and put it over this side, we get, right, that the average value times the interval is equal to the integral. And this is just a statement about two areas. This is this blue area. This is just one number times another. As an area, it's just a rectangle. So here is the base of the rectangle, and here is the height of the rectangle. And that height is the average value. So what we're basically saying is the area of this rectangle is the same as the area on the blue area underneath that curve. Okay, so that means that this stuff here, if we push it down into here, would fill it perfectly. So this is just telling us now that we can make perfect sense of the average value of a function. Okay. So, for example, here is a problem. We've got a function which gives the population of a town. Okay, we recognize it as a population function, right? This is something that grows at a rate of 3.7% per year. And it starts off at 570,000, and it's growing at 3.7% per year. Something nice and solid. And so if we were to graph that, it would look like, well, at T0, which corresponds to the year 2000, we're at 570. And then it grows exponentially. So if we talk about 20 and 40, right, this corresponds to the year 2020. This corresponds to the year 2040. So we want to figure out what the average population of the town is in this period. If we take the integral, we would get this area here. And then the average population would be something like, oh, I've got a different card, so why don't we do this? Oh, no, that's too much. Still not quite great, but anyway. Such that the blue rectangle equals the area underneath here. So the average population equals integral between 20 and 40 of our function, 570 times 1.037 to the t, right, divided by 20. And this makes sense, right? Because this is an integral. This is a rate, this is thousands per year. We integrate it, so that means we multiply the units together. So thousands per year times years equals thousands. So this integral here represents thousands of people. And we divide it by 20. So this is thousands of people per year, which is what an average is, right? It's how many people per year you have. Okay, so at the moment, this is, well, we don't really have formulas yet, so we can't maybe solve this explicitly. What we could do is go out and do an Excel file and come up with a really good estimate for this, and then we divide by 20, and then we actually get the answer. Let's go ahead and do that. Oops. Stop share maybe. Oops, where is my? Must be in the previous week. Here we go. Let's get the Zoom again. Yeah. Okay, so this is the integral file that we had before. And so let's just double check. If we click on this, oops, we see that it's 570 times 1.03 to whatever the thing is. We see that it's the actual right function. A and B, we actually want to be between 20 and 40, right? And so we see two values, the left-hand sum and the right-hand sum. So let's take the average of the two. Let's take equals average of what is it? C21 and D22. And we get as our answer $34,000. So let's say 660,000, right? So that's 34,660,000, right? But that's adding up people over 20 years, and to get the average, we'll then divide by the number of years. And so if we do equals F16 divided by 20, we get that answer there, 1733. And so we get as our approximation that the average population of the town will be 1,733,000 people for that 20-year period. And if we wanted a better answer, we would just change our delta x to something finer and do that, or wait a couple of weeks until we actually learn the formula that gives the answer. That's what we're going to be doing in the next, no, probably the week after. What happened there? Oh. Okay. So that's an example of using an average value. Here's a thing I showed you when we did the lab. Here is a function showing the blood pressure. Okay. So this is an example of a graphical problem. As we know, I can give you a problem numeric. So I'm going to be on the test on Tuesday, I'm going to give you graphical problems. I'm going to give you numerical problems. Okay, and I'm going to give you formula problems. With the formulas, you've got to come up with your own numbers. Okay, so here is the blood pressure. So your heart beats, right? So what happens is your heart pumps and it squishes out the blood, and your blood pressure goes up, and the blood goes out to your, your fingers and your toes and your brain and all that. And so it reaches a maximum, and then it kind of eases back until it's time now for the next squeeze your heart. So here, so when you go to the doctor and they put the clamp around your arm, they tell you, 120/80 or something like that. That's giving you the systolic pressure, which is the peak, and the diastolic pressure, which is this minimum, which is like what happens when your heart is at rest. And the other one is when the heart just does that push. Okay, and so we can see here that it's 120/80 is the two blood pressures, the max and min. And so the average would be 100, right? That's the value that's in between. So that's not your average blood pressure, right? Because we see what happens is that you're at your minimum for much longer than the surge from your actual heartbeat, right? So you don't need to be beating all the time. You do work like if you're doing lots of activity, but usually when you're at rest, your heart beats, goes out, doesn't do anything for a second, and then beats again. That's just what depends upon how much oxygen the body needs. Okay, so we see that the actual average, right, would be the area underneath this curve divided by the length. So it'll be the line that we can draw such that the area under the line equals the area under the blue curve. Okay. And so we should be able to see, just by eyeballing it, that it's going to be less than 100, right? Because this thing, the line at 100, right, there's only a little bit above 100, and there's a whole lot below 100. Okay, and so what would that actual average be? What do you reckon? it's kind of more like, it looks like it's just like a little bit above 90 to me. And maybe I'd guess at 92, but you'd actually need a ruler or whatever to actually get in there. Okay, so that's just an interesting medical fact. Okay, so here, let's just finish off with a few, trying to make sense of these questions. So if we make sense of this question, then I'll make sure that we understand this thing. So we're looking at the average value of sine over an interval. So let me just remind you what sine looks like. So it starts at 0. So what we're going from 0 to 2 pi. So here's pi. Here's 2 pi. And what happens? Okay, we know that sine goes like that, and then it goes below that. Okay, so here's an easy question for you before we answer this question. What's the average value of sine between 0 and 2 pi? Pi. No, between 0, average value of the function. So what's the area under the curve between 0, right? Because wherever it's positive, it's something that counterbalance. So the average value is 0. Okay. So this is a different question. So this is a little bit of a trick question because a lot of people think I'm asking for the integral over those two values. But remember, I'm asking for the average value. So, so for these three things, it's the same thing as the integral, right? Because the interval is both the same. It's like a pi interval. But this is not, right? Because this is a really short interval. Okay, so which is going to be, so we've got 0 to pi and pi to 2 pi. Which one of those averages is going to be the greatest?
0 to pi.
0 to pi, right. So 0 to pi, it's going to be some number. Pi to 2 pi, it's going to be negative that number. Okay, so definitely we can say, we can put A here and we can put C here. What about the average between pi on 2 and 3 pi on 2? Where does that fit with A and C? What is that average value over this interval?
0.
0. Okay, so it has to be here. Right, this is positive something. This is like maybe a half, 0, negative a half. Okay, so what about x between 3.14 and 3.15? So this is like over here. So what's the average value there? So what is pi? Pi is what? 3.14159 something. So afterwards, remember this function goes up. So what can you tell me about this average value here? Yeah, it's going to be greater than 0, right? Because between 3.14 and 3.15, for most of it, it's on the 3.15, right? And so it's going to be more than B. Is it going to be more than A? No, because A is up here. So okay, does that make sense? Okay, so let's see if we can try the same thing with cosine. So cosine, what do we got? We got up to 4.72. 4.72 is around 3 pi, isn't it? No. Hang on, no, let's do this. So what does it do? So cosine goes like this, and then hang on. Oh, no. I've got to remember my. Here's pi on 2 goes to here, and then it goes to here at pi. Here's 3 pi on 2 here, and then it goes up here at 2 pi. Okay, so what do you think the average value is between 0 and pi? So between 0 and pi on 2 is balanced between pi on 2 and pi below here. All right, so that average value is 0. Between pi on 2 and 3 pi on 2, what?
Negative.
It's going to be negative, right? Because the whole thing is down here. So B is negative, and it's negative, say negative a half, something like that. Oh, 3.14 to 3.15 is around here. So what can we tell about the average value there?
Lower than B.
It's lower than B, right? Because it's pretty near -1. So here is D. It's now -1. And then 4.71 is around here. And we'd have to look at the, so it's either going to be less than or greater than. It's going to be approximate that. We have to actually have a look at what pi is to actually determine which one is positive, which one is negative. So the interesting one, I think, is this one here, right? Because it's a really small interval. So the integral is really small, but the average value is still more than this, even though the integral is not as negative as this. Because it's over a small period, the average value is actually greater. Okay, so I think we can stop there. Figure out how to turn this thing off. Bye, Jinru.